Let's review quickly some of the fundamental experiments we've been doing on Wednesday related to magnetic field and electric field generated by that magnetic field. First, again, we have to remember we need to check how the multimeter we use actually works. We can do that with the battery. That's one way. We just have to see the deflection. Is happening to the right. The arm, the needle of this multimeter moves to the right. When the current in this loop made of the battery and the wires like this, the current is counterclockwise. So counterclockwise current makes this multimeter move its needle to the right. And now we can use this fact to study different situations. Well, again, that would be my loop. So clockwise or counterclockwise direction. But instead of using only one loop, I use almost 500 to amplify the signal, and I have a magnet. And now what I'm going to do, I'm going to move this magnet into the coil. And when I move the magnet into the coil, having the north pole directed toward the loop, we observe deflection happening to the right, which means in this situation, the current in this loop also has to be counterclockwise. And now we can answer what kind of a current, clockwise or counterclockwise, is going to be happening in any other situation. Because, for example, if we move it away, we change the direction of the velocity, the deflection changes. If we switch the magnet, now south pole points towards the loop, and we move it in the loop, we observe the deflection happening to the left, to the right. Well, nothing. We know because there is almost no flux in this situation. Fields point like this. This is the loop. And we, of course, could switch the magnet with the coil, well, and move it in and out, keeping north pole or south pole closer to the loop. Or we actually could move the coil or loop. I say loop, I mean coil. I say coil, I mean loop, right? We just change the object which is moving. However, relatively to each other, nothing is different between this case when the magnet is traveling into the coil or when the coil is going closer to the magnet. Well, so to explain all these situations, we just start from the very first fact again. When the magnet is far away from the coil, it means we have relatively low value of the magnetic flux at the location of the loop. The direction of the magnetic field lines is like this into the screen. And when we move it closer, we don't change the direction of the magnetic field lines, so we don't change the value of the polarity, I would say, of the flux. However, what we change is the amount of magnetic field. More flux, more field lines now. And when this is happening, the current we are observing is counterclockwise. So now we just need a method to describe this situation. Ideally, we would have to describe it as an equation algebraically. However, as the first step, we can describe it in terms of pictures. pictorial method, which you're supposed to know by now, is very simple. First, all those experiments related to change happening to the flux of the magnetic field at the location of the coil or loop. If the flux changes, we observe the current. The current tells us that there is electric field generated by changing magnetic field. But we know from a recent experience, charges generate electric field. Moving charges or currents generate what? Magnetic field. So, in this experiment and all experiments like that, two magnetic fields are involved. One magnetic field generated by that magnet, we call it an external magnetic field. And as a result of the change of the flux of the external field, we observe eventually a new magnetic field, induced magnetic field. That's magnetic field generated by the current, which is induced by the change happening to the external magnetic field. So this is a chain of connections. And to describe this chain of connections, we can use pictorial method. We just need to remember the relationship between direction of the current and direction of magnetic field in the loop. And that rule works for any kind of current and any kind of field. That includes induced magnetic field and induced current. So first, we start from a picture which describes the situation before anything had happened. Well, first of all, what parameters should we keep in mind? The location of the magnet, the location of the loop, the orientation of the magnet relative to the loop, the motion of the magnet relative to the loop. Right? All these things tell us something about the direction of the magnetic field and the magnitude of flux at the location of the loop. And that's the first picture which we always draw when analyzing a situation like that. In our experiment, the initial value of the flux was kind of low with magnetic field at the location of the loop because magnet used to be afar from the coil. However, magnetic field lines were pointing into the screen and we drew several circles with crosses. Magnetic field lines into the screen. However, the number of magnetic field lines is small, only 3. So that's the situation number one, initial one. When we bring the magnet closer to the loop, what's happening? We do not change the direction of the magnetic field lines. What we change is the number of magnetic field lines, the amount of the flux to the loop. And to describe that situation, we draw another picture. We just have to add some more field lines directed into the screen. Now we ask ourselves, okay, does any change happen? The answer is yes, which means it must be some induced current in the loop generating the induced magnetic field. And what we want to find out first is the direction of that induced magnetic field. And the rule is simple. The induced magnetic field always tries to slow down the change happening to the external magnetic field. So the induced magnetic field always tries to oppose what? Sometimes some people get confused. The induced magnetic field doesn't oppose, always at least, in external magnetic field. The induced magnetic field opposes changes happening to the external field. Changes. So, what kind of change happening? Stronger field. If you want to slow it down, in which direction should we point the induced magnetic field, which was opposing the change. What do you think?
Same answer really quickly. So what do you think?
Out.
Why?
Because the change is an increase in equilibrium.
Yeah.
So unopposing out.
Opposing the change here would be natural. Trying to oppose the field in this situation. Opposing the change means opposing the field. We'll see sometimes opposing the change means supporting the field. But in this situation, you're absolutely right. Well, I can turn my microphone back on.
The induced magnetic field doesn't want so many magnetic field lines generated by the magnet traveling through the loop. So the induced magnetic field has a direction opposite to the external magnetic field. In this situation, we sometimes say to oppose the change, the induced field opposes the external field. That's not always the case, we'll see. But now what we can say is if magnetic field, induced magnetic field, points out of the screen, we immediately can figure out the direction of the induced current, because current and field are related by the right-hand rule. So this is the last step which we make when we use pictorial method. Initial situation, final situation, what kind of change has happened. Then we say the direction of the induced field out of the screen, and now we take the right-hand rule, we point our thumb in the direction of the induced field, and fingers show the direction of the induced current. And if we had now a multimeter connected to this loop, the induced current is counterclockwise, our multimeter deflects to the right. Not the whole multimeter, only its arm deflects to the right. That's how pictorial method works. Any questions? Because all we have to do now is just cover more examples. First of all, we have only 4 options for any possible situation. We entitle this, 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 or this. Remember, we always can assign an area vector to the loop. And in some situations, it doesn't matter. In some situations, we have to match the direction of area vector with the direction of deflection, positive deflection. And again, our galvanometer always shows deflection to the right for a counterclockwise current in the loop. That means for our galvanometer, area vector of the loop connected to it is supposed to be pointing out of the screen. And for our galvanometer connected like that with this particular choice, the flux into the screen is supposed to be negative. The flux out of the screen is supposed to be positive. The induced field into the screen is supposed to be negative. The induced field out of the screen is supposed to be positive, relative to our choice of the area vector. And again, only 4 choices we might have. External field has a positive flux, external field has a negative flux. Induced field is positive, induced field is negative. What about changes? Well, again, we have only limited number of options. This is our first experiment, the induced field is out because flux was in, more flux in, induced current is counterclockwise. And then we can make something different. For example, what does this picture represent? What kind of experiment? This picture represents an experiment when we move the magnet away. Because initially we have a lot of flux, then we have less flux. And in this situation, well, so one change in the experiment relative to the first situation leads to one change in the final result. Instead of having counterclockwise current, now we have clockwise current, etc., etc. It's a good exercise trying at all situations. Well, one of the examples. We don't have a galvanometer here. However, what we have is a moving loop. Well, I'm going to ask you this question. So how would we use pictorial method? This is how. When the loop is, well, first of all, we need to know the direction of the magnetic field in the loop, right? To do that, we can use the right-hand rule for this current. We grab it with our fingers, with our thumb pointing in the direction of current. So this is the magnetic field lines above this current. Below this wire, magnetic field points into the screen. Above, magnetic field points out of the screen. And the magnetic field strength decreases with distance. So when the loop is here, we have large flux with the field out of the screen. When the loop is here, we have less flux. What change is happening now? Decreasing in flux. And to oppose that change, now induced field supports the external field. So we always have to balance the things, change and field. To oppose, we ask ourselves, what to oppose? The change. So in this situation, the induced magnetic field has the same direction as the external magnetic field. It supports it. So to slow down the change. And now, if the induced field points out of the screen, right-hand rule again gives us immediately the direction of the induced current counterclockwise. You can stop me at any time and ask any question. This situation, again. When the loop is moving parallel to the wire, the amount of the flux doesn't change. If there is no change, which means what? No induced current, no induced field, of course. In this situation, there is no induced field, there is no induced current. This is the question I want to ask you. Same wire, same loop. But now the current gradually increases. So what do you think about the induced current in the loop? Again, if you guess on every time and you always get it correct, then buy a lottery ticket. Did you guess this? What do you get? Interesting. We don't have means we have to go over more experiments and more examples. In this situation, what's the difference between this case and previous cases? The magnetic field lines inside the loop have different directions. Again, above the line, above the wire, magnetic field points out of the screen, below into the screen. So here, what we have is exactly the same amount of flux out of the screen, exactly the same amount of flux into the screen. So the total flux is what? 0. And if we increase or decrease the current, does it change the flux in the loop? No. Because no matter how strong the current is, no matter how strong the magnetic field is, we still have exactly the same amount of the flux out and in, and they cancel each other. So, if initial value of the flux is 0, that's not important yet. We have to compare it with the final value. But the final value of the flux turns out to be 0 too. And now we have to figure out the change. How do we calculate the change? It's always final value minus initial value. It could be a positive number, it could be a negative number. However, in this situation, the change is 0 as well. Which means there is no change, no induced current, no induced magnetic field. So, some changes like this change might not lead yet to this change. If current changes or loop moves, like in the previous example, it doesn't necessarily mean that flux changes. Well, here, the situation is different, of course. Now, the flux changes. When the current increases in value, we initially have weak magnetic field in the loop, strong magnetic field, less flux, more flux. To oppose the change, induced magnetic field should oppose the external magnetic field, should point into the screen. And right-hand rule tells us the direction of the current clockwise. Well, a loop. So we know when we read a problem, we have to look always for most important words. And in this situation, it says there is, period. So in this situation, the magnetic field presents but doesn't change. And nothing else changes. And if nothing else changes, there is no change, no induced current. Now we read it, and magnetic field reduced. So now please take a minute, apply the pictorial method. Figure out the direction of the induced current and choose one of these answers.
It's much easier when you're actually drawing pictures. We call it for reason pictorial method. We have to draw pictures and use our hand in the end. Remember, I have to solve it on my own. Okay, clockwise.
point seems most popular. So in politics, that would mean one thing. In physics, we have to check. And to do that, we have to draw 3 pictures, first, second, third. So initially, well, when magnetic field reduces, that means we have less magnetic field lines in the loop. What is the direction of the magnetic field? Into the page. So we have a lot of magnetic field lines into the page, and now we have just a few, right? So what kind of change is happening? Flux decreases in magnitude. So to oppose the change, the induced magnetic field is supposed to support the field. They should have the same direction. And in this situation, the right-hand rule tells us the direction of the curve. Thank you very much. Indeed it is clockwise. Again, you really have to draw your pictures. Well, before we go to more examples, I would like to do some more experiments. Well, this one, sure. It's a copper pipe. Oh. Where do you look? Oh, copper pipe. And here I have 2 balls. This is the first one. See how fast it falls through it. It's just a regular free fall situation. That's another ball. I have to kind of wait a long time before it actually getting through this pipe. What's the difference? Well, it's a simple difference. This is just a regular ball. This is a magnet. So what is happening? Well, when the regular ball falls into the pipe, it doesn't feel the pipe. When the magnet is falling through the pipe, moving magnet induces magnetic field in a copper pipe, because copper is a conductor. And induced current induces magnetic field, which is interacting with magnetic field of this magnet. And we know that the induced field always opposes the change happening to the external magnetic field. So the induced field slows it down. Well, unfortunately slows it down. Would be nice having a device which would provide some energy basically from nothing. Yeah, we could just put a ball here and it would speed it up and we could get that mechanical energy, but unfortunately it's impossible. The law of conservation of energy forbids this. So slowing down actually consistent with the law of conservation of energy. And this is very expensive. This is very cheap. So I'm just going to give you to play and pass around this. You can see this regular copper pipe. This is a magnet. Takes forever. So it's not a trick. There is another experiment. Well, this is a pendulum, a regular aluminum pendulum. And it swings back and forth, back and forth, back and forth. What I want to do now, I want to take a magnet and make it move between the poles of this magnet. I have a question related to this, so I just want to make sure it's actually getting through. So what do you think is going to happen now if I release this pendulum? It just stops. No magnet, moves back and forth, back and forth. With the magnet, stops. Why? What is happening? Well, again, we know that aluminum is a conductor. So when this aluminum pendulum is traveling through the magnetic field, magnetic flux changes. Changing magnetic flux induces magnetic field, and induced magnetic field always opposes the change. So again, the external magnetic field slows it down. I have a different kind of pendulum like this. It has a lot of cuts. What do you think is going to happen now? Well, this one practically doesn't change. What's the difference between these two? Well, here we can have induced a lot of current, but here, because of the cuts, the current is really weak, so induced magnetic field is weak. So the interaction is much weaker than in this situation. Well, and one more experiment. This is a really, really strong electromagnet. Go wherever. And what I have here, two rings. This is one aluminum ring. It jumps when I turn the current on. This is another one. It doesn't. What's the difference? If you look closely, I don't know if you can see it, there's a cut right here. This ring is cut. This is not. So when I turn the switch on, this electromagnet induces a strong current in this loop. That induced current induces induced magnetic field, and because they oppose, they repel each other. But in this ring, because of the cut, we can't get induced current in it. No induced current, no induced magnetic field, so nothing is happening. My question to you, what do you think is going to happen if I take this ring, not cut, it jumps, but what I want to do now, I want to put it in here. And this is a styrofoam bucket of liquid nitrogen. Liquid nitrogen is really, really cold. Yeah? So it would be unwise to put your finger in it. But if we cool down this ring and we put it back on this electromagnet and we turn the switch on, what do you think is going to happen? What do you think is going to happen? What do you think is going to happen? Anyone? Any suggestion?
It's going to jump more.
Why? heard that. What do you think about it?
I think that it would matter if experimental.
When we cool it down, what kind of properties we change? We've changed many different properties. For example, well, the diameter slightly changes. But in terms of the current, what might be important? The first test has been just 2 weeks ago. You should remember still the relationship between current and other properties of matter, like resistance. Resistance depends on temperature. Higher resistance, higher temperature, more resistance. Lower temperature, less resistance. Less resistance means we can induce higher current. So it does jump higher now. That's it. So we just have proved with this experiment that, first of all, Lenz's law works, and second of all, cooling decreases resistance. Less resistance, more current. More current, higher jump. Any questions? Well, it's Friday, is it? So, Monday can be really boring. I'm going to do all my experiments today. Again, 2 balls, you know, one is a magnet, another is not a magnet. So, what I'm going to do, actually, I'm going to ask you a question. I'm going to erase them. I'm going to place 2 balls on 2 rails and let them go. And which do you think is going to win the race? If you can think about it, I'm going to prepare the system. So, first, magnet wins. Second question. Not a magnet wins. Third question. Is going to be a tie? I don't know. And now I'm going to start falling. And could you please, if you could you please help me? I was just in case catch the ball so it wouldn't roll away. You know what? We don't need so much time, right? Which is which? Okay, so here, magnet. I place it on this rail. And this is just a regular ball. I place it on this rail. Ball start. One more time. And go. Oh well. Come on. Thank you very much. You were really helpful. So, let's see who wins this question. You win this question. Great. Of course, the key word is to oppose. So, every time when we have a magnet interacting with a conductor, induced magnetic field always opposes the change. So in this situation, again, it slows down the motion of the magnetic ball, that's it. And it doesn't act on a regular ball. Great. Well, can start Faraday's law. I'm not going to ask you this question. Just let's figure it out. A loop. Okay, a loop. In a uniform magnetic field, directed out of the page. All right. Magnitude of magnetic field is false. So it actually decreases. So we have to add some more magnetic field lines initially. And now we have to draw just a few magnetic field lines, right? What kind of change is happening? Well, flux decreases. So the direction of the induced magnetic field is supposed to be the same. Because to oppose the change now, it supports the field. And finally, for this particular direction, the right-hand rule gives a counterclockwise curve. Any questions? Well, you're going to be solving many similar problems. You can do it at home. You can do it at home. Now we have a galvanometer. Which kind of galvanometer? Our galvanometer, which deflects to the right with a counterclockwise curve. And here, this wire generates magnetic field. The first question you should ask, what first question should you ask yourself? There are no moving magnets, so it's not about the magnet, but there is always a question we have to ask, what is that pressure? We cannot use pictorial method without drawing pictures. To draw a picture, we need to know direction of the magnetic field. So first question, what is the direction of the magnetic field in a loop? Second question, what is happening to the flux? Well, very quickly. So if this is the current, the right-hand rule tells us the direction of the current, and you have to do it that way. You cannot do it in your head. The direction of the current should be into the screen at the location of the loop. What is happening to the current? Well, in this case, it's increasing. That means magnitude of the field also increases. So we get in more and more magnetic field lines over time. To oppose the change, the induced magnetic field should pointing in opposite direction, which means out of the screen. And for this situation, the current is counterclockwise, and for counterclockwise current, the deflection is to the right. Done. This is another example of a situation where you have to put yourself in the shoes of the observer. Something is happening relative to you. So you have to imagine what is happening, and relative to you, the direction of magnetic field may be towards you or away, and the direction of the current may be counterclockwise or clockwise. It's not relative person who reads the problem, and it's relative to person who are in the problem. Well, this is a very nice experiment. Again, we have two rings, full one and one with a cut. We already know that nothing should be happening when we use a magnet, move it into the ring with the cut, because there is no induced current. So, nothing. But what's going to be happening to this ring? Well, the induced current induces magnetic field, and those two magnetic fields interact. So if I bring the magnet close to the ring, the interaction is supposed to lead to repulsion. But if I try to get it out, the interaction leads to attraction. Because the induced magnetic field always opposes the changes happening to the external magnetic field. And for each situation, we can always apply the pictorial method to figure out what might be happening. Like this. So magnetic field lines go away from the North Pole. But it's far away from the loop. So let's say this is an observer. Relative to the observer, magnetic field lines point directly at him or her. That's what the observer sees initially. And relative to the observer, when magnet getting closer to the loop, more and more magnetic field lines the observer can kind of see. So, relative to the observer, the induced magnetic field is supposed to have direction which same as external or opposite one? Opposite one. And, well, in this situation, that's supposed to be what is it? Induced current. Now, so relative to the observer, this loop now looks like this. South, because magnetic field lines go away from the observer. If this is south, that is acting like a north. So we have two opposite poles, north and north, repel each other. And the last thing to mention, remember I've been moving a coil instead of a magnet. So it doesn't really matter how we change the flux. In this situation, number one, the magnetic field is uniform. So when the loop is traveling like this, the flux stays the same. There is no flux change. Yeah. No change is happening. No change is happening. No induced current. In this situation, when the loop is moved, well, we had a few lines, now we have more lines in the loop, which means now the change of the flux is happening, not zero anymore. Change is happening, we have to observe induced current. And of course we can figure out the direction of the induced current, but there is need connection between the Lenz's law and the right-hand rule describing the force acting on the charges moving the magnetic field. If you have a loop moving in the magnetic field, each electron experiences a force. Yeah. Velocity, magnetic field, force. So what we can see that the force acting on these two electrons is different because magnetic field is not uniform. Because magnetic field is not uniform, the angle is different, the force is different. So these two electrons experience different forces. One force is stronger, and that results in some circular motion of electrons. So that's how the current getting generated in this situation. Well, I guess my time is up, so thank you for coming.